We're going to start talking about molecules. So we've talked about the quantum mechanics of the hydrogen atom, and then and other hydrogenic atoms, things that have just one electron, and then many electrons and how that relates to the periodic table. And now we're going to learn a little bit more about the quantum mechanics of the bonding molecules you should be familiar with from Gen Chem, and then also a lot of orgo and inorganic chem. Okay. So all of Focus 9 is about bonding, so about molecules, how we describe the quantum mechanics of a molecule. So we're going to start with the most basic theory, the first quantum mechanical theory, which was valence bond theory. We'll go through what the important points are. Then we'll talk about molecular orbital theory, which is a better theory and gets better as computers get better because it's not as easy as valence bond. You have to actually do a calculation with a computer in general to figure out the molecular orbitals for a molecule. So we will start with valence bond theory, and I am going to use notes this time just to see if that makes it a little easier for you to see. And I'll also have the book here so I can refer to pages and hopefully bring it all back into context. Okay, so valence bond theory, the first quantum mechanical bonding theory developed. And we should remember this from Gen Chem and then reinforce so much in organic chemistry that in valence bond theory, we say a bond is formed when an electron in an atomic orbital on one atom pairs its spin with that of an electron in another orbital on another atom. So when two atoms sit side by side, if they each have an orbital that only has one electron, those can essentially pair and create a bond. So you want to read the chemist toolkit, which is it's on the very first page. So the chemist toolkit, both 25 and 26. Those will remind you of Lewis structures, which was the first way to describe bonding. And that wasn't a quantum mechanical theory. And you had to join that with Vesper theory, valence shell electron pair repulsion. So just read those on page 391 and refamiliarize yourself. That will help remind you what you do know about bonding with a very simple theory. And the first thing your book says is that all theories for the quantum mechanics of bonding within molecules use the Bohr-Oppenheimer approximation. And most would be a better word, not all, because my research is now in the area of non-Bohr-Oppenheimer quantum mechanics. It's very complex, but a lot of experiments are showing that separating the motion of the nucleus from the electron is not giving you the right answers when it comes to optical and electrical properties of a lot of materials. So the Bohr-Oppenheimer approximation is important, but it's been around since 1927, developed by Max Born and Robert Oppenheimer. And so it is a very popular approximation. It allows us to do calculations that would be very hard otherwise. Trying to do even the simplest systems when you don't use the Bohr-Oppenheimer approximation is very challenging. So let's look. So we are going to use the orbital approximation in valence bond theory. So we're going to say we have a hydrogen molecule, for example, and when the bond forms, it's a result of a wave function on the A hydrogen atom and another one on the B, being occupied either by electron 1 or 2. And the thing with electrons and all fundamental particles is you can't tell them apart. So to really have a complete solution, you have to say one electron is on A and 2 is on B, but then there's also 2 is on A and 1 is on B. So the wave function for valence bond theory is created by adding together the orbitals on each individual atom. So a 1s here and a 1s there. So when the electrons pair their spins, they form a sigma bond. This is just a picture of what the Bohr-Oppenheimer approximation is essentially saying. So the Bohr-Oppenheimer approximation is saying that you have a big heavy nucleus like this cake, and you have bees surrounding it like the electrons. And if you move the cake, the bees will move much, much faster and be right back on that cake wherever you put it. So the Bohr-Oppenheimer approximation takes advantage of the fact that nuclei are heavy and electrons are light, and so their relative motion is very different. So when that bond is formed, we're going to find that we have a potential energy surface that shows you when the bond's formed, we're at a point of minimum energy. So the energy goes down as the particles come together. So if this is internuclear distance, at long distances, the energy isn't as good as at this point. And then if you try to keep pushing them together, the nuclei start repelling each other. And so there's going to be this perfect place at which we say the hydrogen molecule's bond length is optimal. So energy is at a minimum at that RE. And so that's where the bond is. So we have an accumulation of electron density between the nuclei. Let me show you a picture from your book about that. So when you say you have an accumulation, so if we take these two wave functions and the two black dots, so this is figure 3 on page 393, are the nuclei. When the nuclei are at the perfect bond distance, you have a lot of overlap in that probability function between the nuclei. And so we say that with that accumulation of electron density between the nuclei, that helps hold the nuclei together and it lowers the potential energy. This also removes electron density from close to the nuclei, which raises the potential energy. So if an electron really wants to be next to the nucleus and you move it away and put it in that region between the bond, that raises the potential energy. So that's not favorable for the bond forming. And then also, when you put an electron and allow it to move through a whole molecule instead of just around an atom, it has a larger range. So if we think back to the particle in the box, the energy for the particle in a box, its kinetic energy was proportional to 1 over the length of the box squared. So the length of the box gets bigger, the energy goes down. And so this lowers the kinetic energy, and so that's a positive thing. So when we think about bonds forming, it's a playoff between several factors. And if the attractive factors win, you'll have a bond. Not all atoms bond together. So when we talk about the bonding in nitrogen, we can think about if you have two, well, let's first just look at the electron configuration. So it's a 2s2, 2p3. So it's these 3 p electrons that can overlap with another nitrogen. So this is for each nitrogen. So we can think that the first one that's along the bond axis, each of their pz, and I could have called it anything, but I'm saying the bond axis is the z-axis. They overlap to form a sigma bond. And a sigma bond just says it's circular. So it has the same shape as an s orbital because sigma is Greek for s. Then these two, perpendicular to the pz, you're going to have the px maybe coming out of the plane and the py in the plane of the paper. And those overlap sideways, we remember, to form our pi bonds. So when we look at polyatomic molecules, we're going to have the same concepts. It gets a little crazier. So self-test 9A.2 asks us to describe the bonding in ammonia. And so the nitrogen, once again, has a 2s2, 2p3. So you have 3 p orbitals, each with 1 electron. Each hydrogen has a 1s electron. So we can say that each of those p orbitals on nitrogen overlaps with the 1s on a hydrogen to form 3 sigma bonds. They're 90 degrees apart because we know p orbitals are 90 degrees apart. And so it doesn't really match experiment very well. The angle doesn't. So there are 2 major deficiencies in valence bond theory. Number one is you don't really get the right geometry very often. And then the other thing is we often don't get the right number of bonds. So we know that carbon forms 4 bonds in most stable situations. And in order to explain that, we have to look at its electron configuration and say, well, this is full, so it can't form a bond. And we have 2 p orbitals each with 1 electron. How are we going to make methane when we only can form 2 bonds? And how are we going to make methane with 109.5 degree angles if the p orbitals are 90 degrees apart? So we come up with this idea within valence bond theory that we can form hybrid orbitals. And that's totally valid because as you learn more about quantum mechanics, if one function is a solution to the Schrodinger equation for the problem, a linear combination of functions that are also eigenfunctions for the Schrodinger equation for this problem is also a solution. So with methane, we think, okay, take carbon's electron configuration, undergo the process of promotion. So take one of the electrons in the s orbital, give it a little bit of energy, and now you have 3 electrons, each individually in p orbitals and 1 in an s orbital. So now we would have the right number of orbitals to form 4 bonds in methane, but their angles wouldn't make any sense. These would form a different angle than this, and we need them to be 109.5. And so you can think about it that if we add together these, which are solutions to Schrodinger's equation, we add an S and all 3 P's, we add them in different ways, we get hybrid orbitals, and we call these sp3 because they're 1 part S, 3 part P, and they happen to be 109.5 degrees apart. And so those are the orbitals that you would use to describe methane's bonding. We can also think about sp2s and sps, and similar concept, needs to be 1 part S and 2 parts P. So each of these terms is squared. So if you square this, you get 2. Essentially, it says you have 2 P's for every 1 S. And if you add these together, the sum is 2. So you have to have a combination of 1 part S and 2 parts P. And then for the sp hybrids, you need 1 part S and 1 part P. So each of these has a coefficient of 1, so they're 1 to 1. So the hybridization of nitrogen atomic orbitals always results in the formation, not nitrogen, of N, that many atomic orbitals. So if you take 1 S and 3 P's, you have 4, N equals 4 for the number of atomic orbitals. It will always result in forming 4 hybrid orbitals. So the sp3s, there are 1, 2, 3, 4 atomic orbitals added, and we end up with 4 sp3 hybrid orbitals. So the other concept that's important in valence bond theory is the concept of resonance. So it's a superposition of states or wave functions. So it could be a lot of different possibilities, but when we look at something like HCl, the wave function would be a function on the hydrogen and a function on the chlorine, and then just moving which electron is in which of those functions. These would be covalent contributions because you're talking about overlap. But you could also talk about a contribution or a resonance structure where it's an ionic bond. And that would mean that there's an electron on chlorine and another electron on chlorine, leaving hydrogen with none. So when you add these together, so if we add together this covalent part and then the part that's ionic wave function, you can figure out the ionic character by calculating that lambda. So, and there are ways to do that within the molecular modeling software. So that would tell you what contribution ionic resonance structure makes to the structure of HCl. We know clearly, like things like benzene have resonance structures. So that's a very popular concept within valence bond theory. So we summarize what we know about valence bond theory, which is still used today a lot. Sigma and pi bonds are formed by spin pairing of electrons on adjacent atoms, and they're distinguished by their symmetry around the internuclear axis. So sigma has symmetry like a s orbital, pi has symmetry like a p orbital. So you're going to either get a circular shape for the electron density here, or something that looks like a dumbbell when you have the pi bonds. Number two, promotion of the valence electrons. The valence electrons can be promoted to empty orbitals if overall that results in a lowering of energy. So remember, if we look back at carbon, the carbon that we looked at, when we looked at its ground state configuration, it could only form two bonds. And we know when you form a bond, it goes down in energy. So it takes a little energy to do that promotion, but overall, the forming of more bonds will lower the energy more than it took to do that promotion part. So number three, we do that promotion, but then we also talk about hybridization so that we can get the right angles. So the promotion allows us to get the right number of bonds. The hybridization helps us explain the geometry. So atomic orbitals may be hybridized to match the observed geometry of a molecule. And then the last point from valence bond is that resonance. So you can have a superposition of individual structures that distributes multiple bond character over the molecule and lowers the overall energy. And you can also have a superposition and look at the contribution from things like an ionic part to the wave function. So next we'll go into molecular orbital theory. And we'll start with the simplest thing, homonuclear, then we'll go to heteronuclear, diatomics, and then we'll talk about polyatomics.